Welcome back to the Machine Learning 101 course. Today, we will learn how to train an image classification model and learn about a new architecture of neural networks. In the earlier lesson, we learned how to do text classification. First, we convert text into a sequence of tokens that includes terms and phrases in the text. Then, we use the bag of words vectorization technique to feed these variable length sequence of tokens into fixed length numerical feature vectors that can be used for model training. In the last lesson, we introduced neural networks, which is a network of neurons organized in layers. Each neuron is a simple model in and of itself, very similar to logistic regression. To make a prediction, information flows from the input layer to the hidden layer and finally reaching the output layer, which makes the prediction. As part of the training process, the information also flows in the reverse direction in order to update weights between all layers. So far, we've been using scikit-learn, which is a popular Python library for traditional algorithms. Now that we're getting deeper into neural networks, TensorFlow is better suited for the task. TensorFlow itself is quite complex and it would take a while to learn, but Keras, another library built on top of TensorFlow, makes it super easy. We will be using Keras for today's image classification task. A problem to recognize handwritten digits posed by the MNIST dataset can be solved using an artificial neural network, the fully connected one we learned about last time. The image can be flattened into 784 pixels, which will be used as the input features. Since the image is grayscale, each value will be between 0 and 255. In the hands-on exercise, I added two hidden layers, one with 50 nodes and the other with 25. These hidden layers can have either the sigmoid or ReLU activation function, which is another model hyperparameter. And finally, we have an output layer of 10 neurons with the softmax function to give the final probabilities. In the first layer, there are 784 times 50 weights, along with 50 biases, one per neuron. Hence, the total parameters to learn for the first hidden layer is more than 39,000. The second hidden layer is much smaller, with 50 weights for each of the 25 neurons, along with 25 total biases. This adds another 1,275 parameters. Finally, the output layer has 10 neurons, each of which has 25 weights and 1 bias, a total of 260 parameters for this layer. In all, the training process involves learning more than 40,000 parameters using forward and backward propagation. Now, let's look at another architecture that is much better suited for image-related problems.
And this dense neural network will work okay for a simple image like handwritten digit. But when you have a bigger image, let's say this little cute looking koala, the image size is 1920 by 1080. We have 3 as RGB channel here, one for red, green, and blue. In this case, the first layer neuron itself will be 6 million. If you have, let's say, hidden layer with 4 million neurons, you're talking about 24 million weights to be calculated just between the input and hidden layer. And remember, deep neural networks have many hidden layers. So this can go easily into like 500 million or 1 billion of weights that you have to compute. And that's too much computation for your little computer. See, my rabbits are getting electrical shock because it's just too much to do. So the disadvantages of using ANN or artificial neural network for image classification is too much computation. It also treats local pixels same as pixels far apart. If you have koala's face in a left corner versus right corner, it is still a koala. It doesn't matter where the face is located. So the image recognition task is centered around the locality, okay? So if the pixels are moved around, it should still be able to detect the object in an image. But with ANN, it's hard. So how does human recognize this image so easily? So let's go into the neuroscience a little bit and try to see how we as humans recognize any image so easily. When we look at koala's image, we look at the little features like these round eyes, this black prominent flat nose, these fluffy ears, and we detect these features one by one. In our brain, there are different set of neurons working on these different features, and they're firing. They're saying, yeah, I found koala's ears. Yes, I found koala's nose, and so on. Then these neurons are connected to another set of neurons which will aggregate the results. It will say if in the image you are seeing koala's eye, nose, and ears, it means there is a koala's face in the image. Similarly, if there is koala's hands and legs, it means there is koala's body. And there are different set of neurons which are connected to these neurons, which will again aggregate the results, saying that if the image has koala's head and body, it means it is koala's image. Same thing with handwritten digit 9. There are these little edges which come together and form a loopy circle pattern, which is kind of like a head of digit 9. In the middle, you have a vertical line. At the bottom, you have diagonal line. Sometimes you don't have diagonal line at all. But we know that whenever there is a loopy circle pattern at the top, vertical line in the middle, diagonal line in the end, that means digit 9. So how can we make computers recognize these tiny features? We use the concept of filter. In case of 9, we have 3 filters. The first one is the head, which is a loopy circle pattern. In the middle, you have vertical line. In the end, you have diagonal filter. So we take our original image and we will apply a convolution operation or a filter operation. So here I have a loopy circle pattern or a head filter. This filter right here. The way convolution operation works is you take 3x3 grid from your original image and multiply individual numbers with this filter. So this -1 is multiplied with this one is multiplied with this one, and so on. In the end, you get a result, and then you find the average, which is divided by 9 because there are total 9 numbers. And whatever number you get, you put it here. Now, this particular thing is called a feature map. So by doing this convolution operation, you are creating a feature map. So you do it for the second round of 3x3 grid. Here I'm taking a stride of 1. You can take a stride of 2 or 3. Also, you don't need to have 3x3 filter. You can have 4x4 or 5x5 filter. And then you keep on doing this for your entire number. And in the end, what you get is called a feature map. Now the benefit here is wherever you see number 1 or a number that is close to 1, it means you have a loopy circle pattern. So this is detecting a feature. In the case of koala, this will be eye or a nose, because for koala, eye, nose, ears are the features. So by applying loopy pattern detector, I got this one here in my feature map. I also call it the feature is activated. It got activated here. For number 6, it will be activated in the bottom in this area. If you have 2 loopy patterns, the feature will be activated at top and bottom. If you have a number like this, it might be activated in a different area. In summary, when you apply this filter or a convolution operation, you are generating a feature map that has that particular feature detected. So in a way, filters are nothing but the feature detectors. For koala's case, you can have eye detector, and when you apply convolution operation, in the result, see, you got these 2 eyes at this location. If the eyes are at a different location, it will still detect because you're moving the filter throughout the image. And they are location invariant, which means doesn't matter where the eyes are in the image, these filters will detect those eyes and it will activate those particular regions. Here I have 6 eyes from 3 different koalas and they are activated accordingly. Hooray! The hand of koala is in this particular region. Therefore, when I apply hands detector, it will activate here. Now for number 9, and I'm just moving between number 9 and koala so that the presentation is simple enough and you still get an idea. In case of 9, we saw that we need to apply 3 filters: the head, the middle part, and the tail. And when you apply those, you get 3 feature maps. So I applied 3 filters, I got 3 feature maps. And this is how these feature maps are represented if you're reading any online article or a book. They are kind of stacked together and they almost form a 3D volume. In case of koala, my eye, nose, and ear filters will produce 3 different feature maps, and I can apply convolution operation again. And let's say this time the filter is to detect head. By the way, the filter doesn't have to be 2D. It can be 3-dimensional as well. So just imagine this first dimension is representing eyes, and the second slice is representing nose, and third slice is representing ears. And by doing that filter, you can say that koala's head is in this particular region of an image. So you're aggregating these results using a different filter for head, and now this becomes a koala head detector. Similarly, there could be koala body detector. And now we got these two new feature maps where this feature map is saying that koala's head is at this location and koala's body is at this particular location. Then we flatten these numbers. See, in the end, these are like two-dimensional numbers. So we can flatten them. So to convert 2D array into 1D array. And then when you get these two array, just join them together. After you join, you can make a fully connected dense neural network for your classification. Now, why do we need this fully connected network here? Well, you can have a different image of koala. See, my koala is sleeping, he's tired. So now his eyes and ears are at a different location. Look at his ears. See, they're here. For previous image, the ears were in a different location. So that generates a different type of flattened array here. And you all know, if you know basics about neural network, that neural networks are used to handle the variety in your inputs such that it can classify those variety of inputs in a generic way. Here, the first part where we use convolution operation is feature extraction part. And the second portion where we are using dense neural network is called classification.
As we saw, artificial neural networks are not best suited for handling large image inputs. A convolution layer scans over the input data using a learnable 2D or 3D filter to detect and capture spatial patterns in the image. In a typical CNN architecture, there are multiple convolution layers. Initial convolution layers recognize simple features like edges and loops, and as information passes through more layers, the subsequent convolution layers assemble these features to learn more complex features. This solves for the two important ANN limitations when it comes to processing images. One, it leverages the spatial information in the image, and second, the number of model parameters do not depend on the size of the input image. It depends on the size and the number of filters, the number of convolution layers in the overall model architecture, and how we use the pooling layers, something we will learn about in the next video. Often in CNN architecture, a convolution layer is followed by a pooling layer before the output is fed to the next convolution layer or fully connected layer. Let's learn more about the pooling layer in this video.
The first pooling operation is the max pooling. So here, you take a window of 2 by 2 and you pick the maximum number from that window and put it here. So here, check this yellow window, 5, 1, 8, 2. What is the maximum number? 8. So put 8 here. Here, what is the maximum number? 9. So put 9 here. Similarly, here, maximum number in green window is 3. So put 3. So you take the feature map, apply your pooling, and generate a new feature map after the pooling. But the new feature map is half the size. If you look at the numbers, you have reduced your 16 numbers into 4. So it's too much saving in your computation. So how it will look for our digit 9 case when you apply max pooling? Well, you can do a stride of 1. In this case, we did 2 by 2 window and stride of 2. Stride of 2 means once we are done with this window, we move 2 points further, 2 pixels further. In this case, we can do 1 stride. See, this is 1 stride. You get an idea. And we keep on taking max. And this is what we get. When our number is shifted, so see, this is the original number where we got this max pooling map. When number is shifted, you get this pooling map. So still, you are detecting the loopy pattern at the top. So max pooling along with convolution helps you with position invariant feature detection. Doesn't matter where your eyes or ears are in the image, it will detect that feature.
The problem for this lesson's hands-on exercise is to identify the piece of clothing in a 28 by 28 image from the Fashion MNIST dataset. We will also try this problem using both architectures, ANNs and CNNs. The repo has been linked in the description below. Try using CNNs for a very similar problem, the original MNIST dataset. This dataset has 60,000 handwritten digits from 0 to 9, a multi-class classification problem. There are more details in this lesson's problem.md file. To learn more about ReLU activation function and other aspects of computer vision, check out these videos. CNNs we learned about in this lesson are a type of deep learning model architecture. In the next lesson, we will explore deep learning in more detail. We will talk about embeddings, recurrent neural networks, and large language models.